This is where we left off on the previous podcast. We have these equilibrium values of nitrogen dioxide and dinitrogen tetroxide, and at least in 4 out of the 5 sets of data, they're different. And yet there's some mathematical manipulation that we can do to get the values that are in the far right column. So let's just look at one set of data. I'm going to bring down the chemical equation because it's a little easier to see when it's close to what I'm doing. Well, we're going to write out an expression and then set it equal to K. K is our equilibrium constant. And let's look and see how we created this. We're taking the concentration of the products, moles per liter of this gas. It's in the numerator. And then we've divided it by the concentration of the reactant. And we've raised that to the second power. Now the idea comes from kinetics. Equal rates, forward and reverse, and the idea of a reversible reaction. And we're thinking of it as an elementary type step in this context. But you don't have to know that in order to set this up. Products over reactants, and you use the coefficients when you write it out. So let's go ahead and pull the values out. Now, since we're calculating an equilibrium constant, we have to use equilibrium values. And then we'll divide it by the other one, squared. And that's where the 216 came from. Since we use concentrations, if you look in the upper right, and I call this Kc for concentration. You can also have a Kp if you use pressures, and you can have others too, which we'll reveal as the course continues. As far as the temperature there in the upper right, that doesn't come into the calculations, but it is needed because at different temperatures you expect to have different equilibrium constants. So those values for the equilibrium constant in the far right column come from equilibrium values. Let's see about some mathematical manipulations we can do with these. So here's some reaction. A and B reacting to make D and E. I'm going to use concentrations, and I've got a 1 in there just because I'm going to do something else with this in a moment. So when you write it, you take the products, they go in the numerator, and raise to the power of the coefficient. And see in the numerator, I didn't go plus in there, did I? It's multiplication. The reactants, you take those and you put them in the denominator. So it's always products over reactants. And then you use the coefficients in the chemical equation for the powers. Now I'll take that chemical equation in the upper left and then I'll reverse it to make the one on the right. Now since we're using reversible reactions, on one level you look at it and you go, well, who cares? Since it's a reversible reaction, who cares what direction you write it? It shouldn't matter. Well, let's see what happens to the equilibrium equation. So the products are still going in the numerator. And the reactants, they're still going in the denominator. Now look at these two mathematical equations. How are they related to each other? How is KC1 and KC2 related to each other mathematically? They're reciprocals of each other. So there's one manipulation. If you reverse the direction that you've written the chemical equation, then you have to take the reciprocal of the equilibrium constant. And this, one reason for this is, do you want to write it to be seen as going from left to right, or do you want to switch it around so you're reading it differently as far as which ones are your reactants or products? If you do that, then you have to change the value of the equilibrium constant. Another equation. Products over reactants. No addition, subtraction going on in there. Now for that chemical equation, I've multiplied all the coefficients by 2 to get the one on the upper right. From a general chemistry 1 point of view, if you had balanced that equation as it is on the right, you would have looked at that and seen, oh, wait a minute, all those coefficients are divisible by 2. You would have divided them all by 2, and then you would have come up with the equation on the left as the properly balanced equation. But there are times that you may have to do that. Say if you're constructing an equilibrium chemical equation from a number of steps, this may be a needed step. It's still products over reactants. So how are these two related to each other? To go from the left to the right, I multiplied the coefficients by 2, but how does that affect the equilibrium constant? Multiply the coefficients by 2, then you square the equilibrium constant. Now I wrote this. This is if we're using concentrations, moles per liter, which again you can do for gases. Moles of a gas per liter of the gas is fine. But you can also write this out in terms of Kp, which means you'd need pressures. But the mathematical method is still the same. Common units that I've seen for these are atmosphere and bar. Oh, and as far as the units, if you think about what we did earlier, the value for Kc for that reaction was on average 216, no units. No units are used in the equilibrium constant. They're factored out. Let's write another one out. Carbon monoxide reacting to form carbon dioxide and solid carbon. Products over reactants. And I've left something out, haven't I? What did I leave out? I left the solid out. Whenever you write an equilibrium equation, you leave out pure solids and pure liquids. The concentrations of pure solids and pure liquids don't change. If you take pure water, for instance, it's about 55 moles per liter. And regardless of whether you have a small amount or a large amount, the concentration doesn't change. Similar idea with the solids. So you leave them out. Now the actual reason has to do with activities. And we don't even talk about activities in first year chemistry. But the activity of a pure solid and a pure liquid does not change. Regardless. Leave the solids, leave the liquids out, whether it's a Kc or a Kp.